At 7:23 a.m. on March 15, 1943, Staff Sergeant Tommy O'Brien crouched in the mud beside the Chindwin River in Burma, watching 3,000 British civilians flee toward a river that had no bridge. Japanese artillery shells whistled overhead, landing in the jungle 200 yards behind the refugee column. The enemy was closing fast, maybe 6 hours away. The river was 800 meters wide, too deep to ford, too swift to swim. Every boat had been destroyed or captured. The 28-year-old engineer from County Cork had been ordered to find a way across with no materials, no equipment, and no time. His commanding officer, Major Harrison, had given him an impossible task: build a bridge that could handle 3,000 people, plus military vehicles, in less than 4 days. Use whatever materials could be found in the jungle. Ignore the fact that Japanese artillery could range the construction site from across the river. The major had concluded his orders with a grim assessment. "Sergeant, this is probably suicide, but it's the only chance these people have." Tommy stared at the brown water rushing past at 8 knots. Standard British Army engineering manuals specified steel girders, concrete foundations, and at least 3 weeks of construction time for a bridge this size. He had bamboo, rope, and 4 days. Everyone expected him to fail. His own men called the assignment impossible. They were about to be proven wrong. Thomas Patrick O'Brien grew up on his father's farm outside Cork, where emergency repairs couldn't wait for proper materials or engineering consultations. When the tractor broke down during harvest, you fixed it with whatever was available: fence wire, leather straps, stones for counterweights. His father, Sean, had been a carpenter before the farm, and he taught Tommy that the best engineering solutions often came from understanding materials at an intuitive level rather than following textbook specifications. The O'Brien farm sat on 47 acres of rolling hills overlooking Bantry Bay, where Atlantic storms tested every structure against winds that could exceed 80 miles per hour. Sean O'Brien had learned to build things that bent without breaking, using techniques passed down from generations of Irish farmers who understood that rigid structures didn't survive long on the coast. Tommy's earliest memory involved helping his father repair the barn roof after a winter storm in 1919. The conventional approach would have been to replace the damaged timbers with identical materials using standard carpentry joints. But Sean took a different approach. He used green wood that would flex in the wind, connected with leather hinges that allowed controlled movement. The repair looked unconventional, but survived storms that destroyed neighboring buildings, constructed using traditional methods. These early lessons in adaptive construction shaped Tommy's approach to problem solving long before he encountered formal engineering education. He learned to study problems from multiple angles, consider unconventional materials, and design solutions that worked with natural forces rather than against them. Tommy's formal education confirmed what he'd learned informally. Trinity College Dublin, Mechanical Engineering, graduated second in his class in 1936. His professors praised his mathematical ability, but worried about his tendency to ignore established procedures. Professor McKenna wrote in his final evaluation, "Mr. O'Brien demonstrates exceptional problem-solving capability, but his solutions often diverge dramatically from accepted engineering practice. He seems to view regulations as suggestions rather than requirements." The Trinity Engineering program emphasized theoretical principles and mathematical precision, but Tommy's farm background gave him practical insights that complemented his academic training. While classmates struggled to understand stress distribution in complex structures, Tommy could visualize load paths based on his experience with barn construction and tractor repair. His final thesis project involved designing a bridge for Irish coastal conditions, incorporating flexible design elements that most professors considered unnecessarily complicated. Professor McKenna remained skeptical of Tommy's approach throughout his academic career, but couldn't argue with his mathematical competence. Tommy's calculations were always correct, even when his methods seemed unorthodox. The assessment proved prophetic during Tommy's early Army career. After enlisting in 1939, he was assigned to the Royal Engineers and sent to France with the British Expeditionary Force. During the retreat to Dunkirk, Tommy's company was ordered to destroy bridges to delay German advance. Standard procedure required explosives placed at specific structural points to ensure complete destruction. Tommy suggested a different approach, partial demolition that would slow enemy vehicles without making the bridges unusable for British forces if the tactical situation changed. The suggestion reflected Tommy's understanding that military engineering often required solutions that served multiple purposes simultaneously. Complete bridge destruction followed military doctrine, but eliminated strategic options for friendly forces. Partial demolition preserved tactical flexibility while still achieving the primary objective of delaying enemy advance. His commanding officer, Captain Davies, initially rejected the suggestion. Military engineering manuals were clear about demolition procedures, and deviation from established protocols could result in court-martial if the modifications proved ineffective. Follow the manual. Complete destruction only, no unauthorized improvisation. But when Tommy's unit reached the bridge at Lille, they found their explosive supplies reduced to half the specified amount due to logistical failures during the chaotic retreat. Standard demolition procedures couldn't be executed with insufficient explosives. Tommy's modified demolition plan became the only viable option for achieving any level of bridge destruction. The technique involved calculating the minimum explosive placement required to weaken critical structural members without destroying them completely. Tommy's mathematical analysis identified load-bearing elements that could be damaged enough to prevent vehicle crossings while leaving the basic structure intact for potential repair by friendly forces. The bridge was weakened enough to collapse under the weight of German tanks, but remained passable for British foot soldiers during the night withdrawal. The technique achieved both objectives, delaying enemy mechanized advance while preserving strategic mobility for friendly infantry forces. The technique worked so well that Tommy was reassigned to special engineering duties immediately after the Dunkirk evacuation. His new role involved developing improvised solutions for situations where standard engineering practices couldn't be applied due to material shortages, time constraints, or tactical requirements. The assignment took him first to North Africa, where desert conditions presented unique challenges, then to Burma, where jungle warfare created problems that European engineering hadn't anticipated. North Africa taught Tommy about engineering in extreme environments where conventional materials deteriorated rapidly and supply lines were unreliable. Desert construction required techniques that could handle temperature extremes, sandstorms, and water scarcity. Tommy developed methods for creating strong concrete using minimal water, building structures that could withstand sand erosion, and maintaining equipment under conditions that destroyed conventional machinery within weeks. But Burma presented challenges unlike anything Tommy had encountered in Europe or North Africa. The monsoon climate rotted wood within weeks and corroded metal within months. Traditional construction materials were unavailable, and supply lines were virtually non-existent during large portions of the year. Enemy action made conventional construction timetables impossible, with projects that would normally take weeks needing to be completed in days or hours. But Burma also offered resources that European engineering hadn't considered. Bamboo grew everywhere, in sizes and strengths that varied dramatically based on species and growing conditions. Some varieties could support tremendous loads when properly utilized, offering structural capabilities that exceeded many traditional construction materials. Local populations had been using bamboo for construction for centuries, developing techniques that weren't documented in any British engineering manual. Tommy spent his first 3 months in Burma studying indigenous construction methods with the same systematic approach he'd applied to academic engineering. He learned which bamboo species provided the best tensile strength, how to treat bamboo joints to prevent rot and insect damage, and how to calculate load distribution for bamboo structures using engineering principles adapted from steel and timber construction. His notebooks filled with sketches and mathematical calculations that combined traditional engineering principles with locally developed construction techniques. He documented joint construction methods, load-bearing calculations for different bamboo species, and structural designs that used bamboo's natural flexibility as an engineering advantage rather than a limitation. The knowledge proved invaluable when the Japanese began their offensive toward the Indian border in early 1943. British forces found themselves conducting fighting withdrawals across terrain where infrastructure had been minimal to begin with and was being systematically destroyed by both sides as the tactical situation changed rapidly. Tommy's unit was attached to refugee evacuation operations in March 1943 when thousands of British civilians who had remained in Burma during the early phases of the war were finally forced to flee toward India as Japanese forces advanced. The evacuation route crossed multiple rivers, many of which had no permanent bridges or had bridges destroyed during the fighting. The Chindwin River crossing presented the most serious obstacle encountered during the evacuation operations. The river was 800 meters wide at the crossing point, too wide and swift for fording even during the dry season, and far too deep for wading with current water levels. Japanese forces were advancing from 3 directions simultaneously, and aerial reconnaissance indicated they would reach the crossing point within 48 to 72 hours maximum. 3,000 civilians, mostly women, children, and elderly men, needed to cross before enemy arrival. The group included British colonial administrators, missionaries, plantation managers, and their families who had remained in Burma during the early phases of Japanese occupation, but were now forced to flee as enemy control consolidated. Standard British Army engineering would have required steel girders transported from India by truck convoy, concrete foundations poured and allowed to cure for at least a week, and construction crews working with heavy equipment for a minimum of 3 weeks. Tommy had none of those resources and a tiny fraction of that time. but he had bamboo growing throughout the surrounding jungle, rope and cable that could be salvaged from abandoned military and civilian sites, and local workers who understood jungle construction better than any British engineer. More importantly, he had an idea that violated every principle of conventional bridge construction, but might actually work given the specific constraints he faced. Traditional bridges were designed as rigid structures that transferred loads through solid beams to stable foundations, resisting environmental forces through structural strength and mass. The approach worked well for permanent construction where materials and time were available for proper foundation preparation and structural assembly. Tommy proposed something completely different, a flexible bridge that would absorb and distribute loads through controlled movement rather than rigid resistance. Instead of fighting the river's forces and environmental stresses, the bridge would work with them, using flexibility as a structural advantage rather than trying to overcome natural forces through engineering brute force. The concept required rethinking fundamental assumptions about bridge construction that had dominated military engineering for centuries. Instead of maximizing rigidity, Tommy's design would optimize flexibility within carefully calculated limits. Instead of concentrating loads on a few critical structural members, the design would distribute forces across multiple interconnected elements that shared stress loads dynamically. The approach required bamboo selection based on flexibility characteristics rather than just absolute strength ratings. Tommy needed poles that would bend under load without breaking, returning to their original shape when the load was removed. The material had to function like a biological shock absorber, absorbing energy through controlled deformation while maintaining structural integrity under repeated stress cycles. He spent the first day testing different bamboo species, calculating stress tolerances for various pole diameters and lengths, and working out the mathematical relationships between flexibility, load distribution, and overall structural integrity. The calculations required adapting standard engineering formulas for materials that weren't covered in British Army engineering manuals. His calculations covered 12 pages of notebook paper with equations that combined traditional structural engineering with materials science principles that wouldn't appear in British engineering textbooks for another 20 years. Tommy was essentially inventing flexible bridge theory under combat conditions using materials that weren't covered in any engineering manual he'd studied. The mathematical analysis had to account for multiple variables simultaneously: bamboo strength characteristics under different loading conditions, joint design requirements for flexible connections, load distribution patterns across a complex web of interconnected structural elements, and dynamic response characteristics under conditions ranging from steady pedestrian traffic to artillery shock waves. The actual construction began on March the 16th at dawn, with Tommy organizing his workforce into specialized teams based on the complex requirements of flexible bridge assembly. Bamboo cutting teams selected poles according to his precise specifications regarding diameter, length, and flexibility characteristics. Rope preparation teams created the intricate web of connections that would hold the structure together while allowing controlled movement under load. Foundation crews prepared distributed anchor points on both sides of the river that would spread structural loads across multiple attachment points rather than concentrating forces on traditional foundation systems. The anchor points represented the most critical engineering challenge of the entire project. Traditional bridge foundations relied on deep pilings driven into riverbank substrate or massive concrete pads that provided stable, immovable attachment points for bridge superstructure. These conventional foundation systems transferred bridge loads to solid ground through rigid connections that didn't allow movement. Tommy couldn't dig deep foundations in the riverbank soil, which geological analysis revealed was mostly sand and clay layered over bedrock that was too deep to reach with available excavation equipment. The soil wouldn't support conventional anchor systems that concentrated bridge loads on a few critical attachment points. Instead, he designed a distributed anchor system that spread the bridge's load across multiple attachment points, extending back from the riverbank into the jungle, where soil conditions were more stable and natural anchor points were available. The system used living trees as primary anchors, with loads distributed through a network of bamboo and rope connections that extended 50 meters back from each riverbank. The design transferred bridge weight to dozens of individual anchor points rather than concentrating forces on a few critical connections. If any individual anchor failed due to soil conditions or enemy action, the load would redistribute automatically to the remaining attachment points without compromising overall structural integrity. Construction proceeded around the clock with work teams rotating every 6 hours to maintain progress while managing worker fatigue under extremely difficult conditions. Japanese artillery fire began reaching the construction area on the afternoon of March 16th, forcing Tommy to modify his construction schedule to minimize exposure during periods of maximum enemy observation. Critical structural work was performed during early morning hours, when mist rising from the river provided natural concealment from enemy observation posts across the river. Less critical assembly work was done at night, when artillery fire was typically lighter because enemy forward observers couldn't adjust fire accurately without visual confirmation. The bamboo poles had to be cut to precise lengths calculated for specific positions in the overall structural network, then joined using traditional lashing techniques that Tommy learned from local workers who had generations of experience with jungle construction methods. Each joint required specific rope configurations that would hold under stress while allowing the controlled flexibility essential for the bridge's dynamic load distribution characteristics. Tommy's engineering calculations specified exactly how much play each joint needed to allow for the bridge's flex response characteristics under different loading conditions. Too little flexibility would cause joint failures when the bridge moved under load. Too much flexibility would allow excessive movement that could make the bridge unusable or create resonance conditions. By the evening of March 17th, the basic structure was in place, a curved suspension system that spanned the 800-meter river width using bamboo poles connected in a complex web of flexible joints that distributed loads dynamically across the entire structural network. The bridge surface consisted of bamboo planking lashed to the suspension framework with spacing that allowed water drainage while providing solid footing. But the bridge hadn't been tested with significant loads, and Tommy's mathematical models were based on theoretical calculations rather than empirical data. No one had ever built a flexible bamboo bridge of this size using these specific techniques. The design could work perfectly according to calculations or collapse catastrophically when subjected to the weight of 3,000 people plus military vehicles. Testing began on the morning of March 18th, with small groups crossing at carefully spaced intervals to assess bridge performance under controlled loading conditions. Tommy positioned himself at the center of the bridge span, where stress concentrations would be highest. If the bridge was going to fail, he wanted to observe exactly how the failure occurred so that emergency modifications could be attempted. The first test group consisted of 5 soldiers carrying standard equipment, weighing approximately 200 pounds per person. The bridge flexed noticeably under their weight, bending in a gentle curve that absorbed and distributed the load exactly as Tommy's calculations had predicted. The bamboo joints creaked audibly as they adjusted to the load, but held firm without any visible signs of stress concentration. The soldiers reported that walking across felt stable and secure despite the visible movement of the bridge structure. The controlled flexibility created a springy sensation underfoot, but the surface remained solid, and the movement felt controlled rather than dangerous. Successive tests used larger groups and heavier loads to assess bridge performance under increasing stress conditions. 20 people crossing simultaneously, 50 people, 100 people plus a military jeep weighing 2,300 pounds loaded with equipment. Each test confirmed that the bridge's flexible design was working as intended, absorbing loads through controlled movement while maintaining structural integrity. But the real test came on the afternoon of March 18th, when Japanese artillery began targeting the bridge directly. Enemy spotters had identified the crossing point from observation positions across the river and were directing concentrated fire at the structure using 105mm howitzers positioned approximately 3 kilometers east of the river. Artillery shells landing in the river created massive waterspouts that subjected the bridge to shock loads far beyond anything Tommy had calculated for during his design analysis. The explosions created pressure waves that hit the bridge structure like giant hammer blows, testing the flexible design under extreme dynamic loading conditions. The first near miss occurred at 3:47 p.m. when a Japanese 105mm shell landed 30 meters upstream from the bridge center. The explosion sent a column of water and mud 40 feet into the air, and the shock wave hit the bridge structure with enough force to destroy a conventional, rigid bridge instantly. Tommy watched from the center span as the entire bridge flexed dramatically under the shock load, bending almost to what appeared to be the breaking point before snapping back to its original configuration like a giant bowstring. The movement was violent but controlled, absorbing the explosion's energy through structural deformation rather than trying to resist the force through rigid construction. A steel or concrete bridge would have been destroyed immediately by that kind of shock loading. Rigid structures transfer shock forces directly to foundation points, creating stress concentrations that exceed material failure limits. Tommy's flexible bamboo design absorbed the explosion's energy through controlled movement across the entire structural network and survived intact. The bridge was actually strengthened by surviving the artillery test because it demonstrated that the flexible design could handle extreme loading conditions that would destroy conventional bridges. The successful shock test proved that Tommy's mathematical analysis had been accurate and that the construction techniques were sound even under combat conditions. Word spread rapidly through the refugee column that the bridge could handle artillery explosions without collapsing. Civilian morale improved dramatically as people realized they had a realistic chance of escaping across the river before Japanese ground forces arrived. The psychological impact of the successful artillery test was as important as the engineering validation. The mass crossing began on the morning of March 19th, with the most vulnerable refugees crossing first: children, elderly civilians, injured people who needed assistance with mobility, and pregnant women who couldn't be expected to move quickly if evacuation became a fighting withdrawal. Tommy established a traffic control system that regulated the number of people on the bridge at any given time to prevent overloading while maximizing throughput. The bridge handled steady streams of civilians throughout March 19th and into the night, with people crossing continuously in groups of 30 to 40 at intervals designed to maintain optimal loading without exceeding structural limits. By dawn on March 20th, over 2,000 people had crossed successfully without any significant structural problems or civilian casualties. The remaining refugees included the strongest adults who could assist with bridge maintenance and emergency repairs if needed during the final crossing phase, plus essential personnel who were coordinating the evacuation and couldn't leave until all other civilians were safely across the river. Japanese ground forces reached the east side of the river at 11:30 a.m. on March 20th, establishing observation and fire positions approximately 400 meters from the bridge approach. Tommy could see enemy soldiers through binoculars as they set up machine gun positions and prepared to interdict the remaining evacuation traffic. Direct small arms fire began hitting the bridge structure at 11:45 a.m., with bullets splintering bamboo poles and severing rope connections throughout the bridge network. The damage was serious, but not immediately catastrophic because the distributed structural design allowed the bridge to function even with multiple damaged elements. The final phase of the evacuation became a race between refugee crossing speed and the rate of bridge damage from sustained enemy fire. Tommy organized repair teams that worked continuously to replace damaged bamboo sections and retie severed rope connections, maintaining bridge functionality while civilians completed their evacuation. The repair work had to be done while under direct enemy fire, with workers exposed on the bridge structure while enemy marksmen targeted anyone attempting maintenance activities. Several repair team members were wounded by rifle fire, but the work continued because bridge functionality was essential for completing the civilian evacuation. The bridge remained functional, but was visibly deteriorating under the sustained enemy fire. Bamboo poles were being shattered faster than they could be replaced, and rope connections were being severed systematically by rifle fire directed specifically at critical structural joints. The last group of civilians crossed at 2:15 p.m. on March 20th, completing the evacuation of all 3,000 refugees with 0 civilian casualties during the river crossing phase. As the final refugee reached the West Bank, Tommy prepared to destroy the bridge to prevent Japanese forces from using it for their own river crossing operations. He had positioned explosive charges at key structural points throughout the bridge network that would sever the main support cables and drop the center span into the river, making the structure completely unusable for enemy purposes while conserving explosives by using the bridge's own weight to complete the destruction process. But as Tommy prepared to detonate the charges, he received unexpected orders over the radio from British military command. British and Indian forces were planning a counterattack across the river that would require crossing in the opposite direction within 48 to 72 hours. The bridge needed to remain intact for potential military use during the planned offensive operations. Tommy faced an impossible choice between conflicting military requirements. Standard doctrine was clear: destroy infrastructure to prevent enemy use, particularly bridges that could facilitate enemy advance toward friendly positions. But the tactical situation was fluid, and the bridge represented a strategic asset that might prove crucial for future British operations. Tommy made a decision that violated direct orders, but reflected his engineering assessment of both military requirements and structural possibilities. Instead of destroying the bridge completely, he would partially demolish the center span using selective explosive placement that would make the structure unusable for immediate enemy purposes while preserving the possibility of rapid repair if British forces needed to cross during future operations. The technique required precise, explosive placement that would weaken critical structural members without destroying them completely, using the same mathematical principles that had guided his bridge demolition work during the retreat from France. The bridge would collapse under the weight of vehicles or large groups of soldiers, but could potentially be repaired quickly by engineers who understood the original construction techniques. The partial demolition was completed at 3:45 p.m. on March 20th, just as Japanese advance elements reached the bridge approach on the east bank and began assessing the structure for immediate tactical use. Enemy soldiers could see that bridge structure remained largely intact, but couldn't determine whether it was functional enough for military crossing operations without conducting dangerous reconnaissance across the potentially damaged span. Tommy's engineering gamble worked exactly as intended. Japanese forces spent 3 days attempting to assess and repair the bridge for their own use, giving British forces time to organize defensive positions on the west bank of the river and prepare for the anticipated enemy crossing attempt. When Japanese forces finally got the bridge functional enough for limited vehicle crossings, British artillery was in position to destroy it completely using conventional demolition methods. The tactical delay achieved by Tommy's partial demolition proved crucial for the overall defensive campaign in the region. Japanese forces lost the momentum they needed to reach the Indian border before British reinforcements arrived from other theaters. The offensive that was supposed to cut British supply lines instead became a costly stalemate that exhausted Japanese resources in Burma without achieving strategic objectives. But the immediate success was measured in different terms. 3,000 British civilians who had been trapped behind enemy lines were safely evacuated to India with 0 casualties during the river crossing operation, demonstrating that innovative engineering approaches could achieve seemingly impossible objectives when conventional methods were inadequate. Tommy's flexible bridge design had achieved something that conventional engineering couldn't have accomplished under the same constraints. By abandoning rigid construction principles and embracing controlled flexibility, he'd created a structure that was actually stronger under stress conditions than traditional designs would have been. The engineering principles that Tommy developed during the Chindwin River crossing were documented in a comprehensive technical report that he submitted to British Army Engineering Command in April 1943. The report included detailed mathematical calculations, construction diagrams with precise specifications, materials lists for different bridge sizes, and specific recommendations for applying flexible bridge techniques in similar tactical situations. Military engineers initially dismissed the report as an interesting anomaly with limited practical application beyond the specific circumstances that had required its development. Flexible bridge theory contradicted fundamental principles that had governed military construction for centuries, and the techniques worked in Burma because of specific local conditions that were unlikely to be replicated elsewhere. But as the war continued and similar challenges emerged in other geographic areas, Tommy's techniques began to be taken more seriously by military engineers facing comparable problems. American forces in the Pacific encountered river crossing challenges that conventional engineering couldn't solve within tactical time constraints imposed by rapid advances against Japanese positions. Flexible construction methods offered potential solutions for situations where standard approaches were inadequate due to material shortages, time constraints, or environmental conditions that made conventional construction impractical. The techniques were particularly valuable for temporary construction that needed to be completed quickly and function reliably under combat conditions. By 1944, modified versions of Tommy's flexible bridge design were being tested by military engineering units in multiple theaters, adapted for different materials and environmental conditions while preserving the basic principles of controlled flexibility and distributed load sharing that had made the original design successful. Tommy continued his engineering service through the end of the war, participating in operations across Burma, Malaya, and the Dutch East Indies. He developed additional construction techniques that became standard procedure for British engineering units operating in jungle environments. After the war, Tommy returned to Ireland and established O'Brien Construction Company, specializing in challenging projects where conventional engineering approaches were inadequate. His company developed a reputation for solving impossible problems using innovative techniques derived from his wartime experience. Tommy's most famous post-war project was the Blasket Islands Emergency Bridge, built in 1952 using techniques derived from his Burma experience. The project demonstrated that flexible construction principles had practical civilian applications. In 1963, Professor David Collins from Trinity College contacted Tommy about documenting his techniques for academic study. The collaboration resulted in published papers that established flexible construction as a legitimate field of engineering study. Tommy's work was cited in research that eventually led to modern cable-stayed bridges and other flexible structural designs, now common in civil engineering, demonstrating the long-term impact of innovations developed under combat conditions. Thomas Patrick O'Brien died in 1978 at age 63, survived by his wife Mary and 3 children. His obituary mentioned his wartime service and successful construction company, but made no reference to the flexible bridge techniques that had influenced modern structural engineering. In 1998, the Institution of Civil Engineers established the O'Brien Prize for innovative engineering solutions developed under emergency conditions, recognizing engineers who demonstrate exceptional problem-solving capability when conventional approaches are inadequate. March 15, 1943, a river in Burma. One Irish engineer with bamboo poles and rope, tasked with building an impossible bridge that everyone expected to fail. 4 days later, 3,000 people walked safely across a structure that shouldn't have worked according to any engineering textbook. Tommy O'Brien proved that the best engineering solutions often come from abandoning established procedures and thinking creatively about materials, time constraints, and load requirements when lives depend on finding solutions that work rather than solutions that conform to academic theory. 800 meters of bamboo and rope, 3,000 precious lives saved, and the vital realization that innovation matters more than regulation when people are depending on you to find a way across